We have been given the task of designing and manufacturing a robot to compete in the modified version of the F180 Robo Cup Small Size League tournament. The Robo Cup Small Size League started in 1997. It attracted teams from all around the world to test their AI systems in a dynamic environment of a simulated soccer field. The goal is, by 2050, to have developed a team of fully autonomous humanoid robot soccer players that can win an official game of soccer governed by FIFA rules. All robots entered into the QUT modified version of the F180 Robo Cup must comply with the official rules to be able to retrieve the ball, dribble the ball, shoot goals within an unknown scene. The allowed budget for the project must not exceed $140 and all subcomponents must be completed within the semester timeframe. The competition environment will consist of a square-shaped playing field with a 2x2 meter area. The robot itself must have a diameter of 180 mm and not exceed the maximum height of 225 mm and be predominantly black in color. Additionally, when viewed from above, the convex hull of the robot must not cover more than 20% of the ball. The robot must be able to consistently move towards the goal and kick 2 goals per minute while avoiding obstacles on the field. And finally, the robot is made from several subsystems including drive system, kicker and dribbler, vision, and artificial intelligence.
I was responsible for designing the drive system of the soccer robot. The robot operates using a differential drive system, which means the robot has 2 driving wheels that operate on independent actuators. The rotation of the robot is actioned by each wheel spinning in the opposite direction of the other. The speed and direction of the robot is controlled by code written on the Raspberry Pi. Commands from the Pi travel through a H-bridge motor driver, which controls the PWM signals to actuate the motors, with speed being adjusted by changing the duty cycle value. The duty cycle would be adjusted manually for the desired speed. As specified by the RoboCup rules, the robot was designed to be able to move forward, backward, left, and right at a speed of 0.05 to 0.2 meters per second. This was implemented to maximize maneuverability without compromising accuracy.
I was responsible for the kicker and dribbler systems. The dribbler was powered by a generic 130 size motor. The drum was rubberized with a parabolic shape to automatically center the ball for kicking. The robot was able to maintain possession of the ball while traveling across the field, rotating and even reversing. For the kicker, a linear solenoid was used. This was chosen over a rack and pinion alternative for vastly reduced mechanical complexity and reliable actuation. The supply voltage was boosted and stored in large capacitors. The solenoid was able to deliver a high power kick, propelling the ball to a velocity of 2.3 meters per second. A regulator was also designed to supply 5-volt power to the onboard systems.
I was responsible for development of the vision system of our soccer robot. Development of our necessary code was made through Python 3 and with use of OpenCV2 image processing libraries. To determine object sizes and types, thresholding values were ascertained through customly developed software. These thresholds were then applied to the frames gathered from the Python camera, creating masks to be manipulated through cost-effective image processing techniques, creating our necessary contours. Through trigonometric principles, object size measurements, and focal point information of the Pi camera, distances and angles were calculated based upon the centroid of these contours. This information was then relayed through vectors to the navigation system, allowing for movement of the robot with a vision system capable of a high refresh rate.
For the artificial intelligence and AI systems, the code base was merged in parallel with the vision system. A finite state machine was implemented, which uses changes from the raw data gathered from the vision system. Reactive navigation was employed to avoid obstacles in real time. Potential field systems were implemented using attractive, repulsive, and residual field vectors, which would calculate the best course for the robot. The robot's navigation was triggered using VNC software for the complete autonomous movement of the robot. Multi-dimensional robot models were used to determine movement after computing vision data. The robot navigated autonomously and managed to score multiple goals in the desired goal of either blue or yellow. The AI and navigation system was successful in playing the modified version of QUT's F180 League.